Hello friends, right now we are going to do the third uh, parameter which we need to study with regarding to the trends in terms of the atomic size. Now, before we start looking at the trends for this particular factor, which is called as ionization energy or ionization enthalpy, we we first need to understand what is the meaning of the term ionization enthalpy, right? So let us define what is ionization enthalpy, and only after that we will be in a correct position to understand the trend. Ionization enthalpy basically means that is, if in case you have an electron which is present in the valence shell of any atom, and if in case you want to remove that electron which is present in the valence shell of an atom from that atom, in that case there will be some amount of energy which will be spent, right? And that energy which is spent in removing an electron from an isolated gaseous atom or ion in its ground state is called as the ionization enthalpy. Now, why do we insist on the gaseous state in the definition? The reason for that, my dear friends, is that when we are talking about gaseous state, there is very less interference of the other atoms when we are trying to remove an electron from the valence shell of an atom. There will be very less interference of the other atoms, because in gaseous state, as we have already seen, the gaseous atoms and molecules, they are very far away from each other. The intermolecular force of attraction in the case of gaseous state is extremely small, and hence we prefer to remove the electron in the case of gaseous states. Second situation is, why do we use the term ground state? Because we don't want the electron to go into excited state, because if in case it goes to excited state, then we would not be able to calculate the total amount of energy which is required to remove that electron. Because if in case it goes to excited state, its energy, the energy of an electron, it increases, and hence its stability, it decreases. And because its energy is already increased and its stability is less, it is easier to remove that electron. When I say it is easier to remove that electron, it means obviously less amount of energy has to be supplied to remove that electron. Hence the ionization energy in the case of excited state electrons will be lesser as compared to the ionization energy required to remove electrons from the ground state. The second very important reason why we do not include the term excited state when we are defining ionization enthalpy is that the excited state of an electron is not fixed, right? When it is in excited state, it can have any energy. It can have lesser energy also, it can be higher energy also. So we require a specific standard from which we can find out the ionization energy, and the perfect standard will be when the electrons are in the ground state. So this was the fundamental groundwork which was required for us to understand the meaning of ionization enthalpy, so that we could start with understanding the trends in ionization enthalpy. So what is the ionization enthalpy? It can be defined as the total amount of energy which is required to remove one electron from the valence shell of a free gaseous atom or ion in its ground state, or the ground state of the atom or ion. So once we have understood what is the meaning of ionization enthalpy, that is the amount of energy required to remove a valence electron, that we now can start with understanding the ionization enthalpy values of all the elements, say from 1 to say atomic number 60 or 70 or 80. So if in case you want to find a trend between the atomic numbers and the ionization enthalpy, then this will be the trend which is observed. As you can see, the trend is not a straight line graph, that is, it is not decreasing straight as we move from as we increase the atomic number. Normally we are used to having a situation wherein we give a rough statement, we give a blanket statement that there will be, as we move from up to down in the periodic table, the ionization energy, say for example, increases or decreases, whatever. As we move from left to right, the ionization enthalpy increases or decreases. we give a blanket statement, right? But in real life, my dear friends, everything is very complicated. It's not that simple. So here also, as you can see, we can see a trend that it is decreasing, right? As we move from atomic number increases, we see that in general it is decreasing. But again, the decrease is not a perfect straight line. There will be increases and decreases in these. So let us, before studying these things in detail, let us look at exactly what happens when we try to find out the ionization enthalpy as we move from left to right in a particular period. That is, say for example, as we move from left to right, in the case of sodium to, say for example, chlorine, what will happen, or say from sodium to finally argon. Let us see what will happen to the ionization enthalpy. For us to understand what will happen to ionization enthalpy and for us to study it scientifically and perfectly, professionally, we have got to understand the effect of all the factors which affect ionization enthalpy. So the first factor which affects ionization enthalpy, let's write it down as we always do. The first factor will be, and the most important factor will be, the number of shells which are involved, which are present in the particular atom that we are looking to find out the ionization enthalpy of. After we finish the number of shells, the next factor will be in terms of the effective nuclear charge. Cut. Editors, I had to stop the last video because this marker was not working. So just restart this video after this point. Start. So the second factor, my dear friends, which will be affecting the ionization enthalpy will be the effective nuclear charge, as we have already seen, right? The third factor which will be affecting the ionization enthalpy will be the screening effect. And finally, we will be having the inter-electronic repulsion. So I've written down all the factors. We'll have to check about which factors affect each specific atom that we consider the ionization enthalpies of. So before going ahead, we need to understand that when we talk about ionization enthalpies, there can be such thing as the first ionization enthalpy, second ionization enthalpy, third ionization enthalpy, and so on. Let us look at what is the meaning of first, second, third ionization enthalpy, and so on. We need to understand by considering an example. Let us consider an example in the case of say aluminium. When we talk about aluminium, we can have a situation wherein we have an aluminium atom whose electronic configuration is equal to 283, right? Because the atomic number being 13. Hence, this aluminium atom, it will give away one electron and it will form Al 1 plus because it has given one electron. So, because we have removed this electron, this valence electron from aluminium, the amount of energy which is required to remove this valence electron of aluminium, that will be the first ionization enthalpy. Let's write it down. This will be the first ionization enthalpy. What we can do is that once we have got aluminium ion like Al 1 plus ion, we can also remove another electron from it. So let's see. Now aluminium now has an electronic configuration of 282, and now with its electronic configuration 282, we try to remove one electron further. Once you do that, you will be getting Al2 plus one electron, and this will be the second ionization enthalpy. And after that, you can also try to remove a further electron from aluminium. So this will be 281 when its electronic configuration will be. You can remove its one electron further. Now aluminium, aluminium 2 plus will now become Al 3 plus plus 1 electron. And because you have removed aluminum's electron for the third time as compared to the starting point when we had considered aluminum atom, because now the third electron has been removed, the total amount of ionization enthalpy will be called as the third ionization enthalpy. In a similar way, we can find out the fourth ionization enthalpy also, but right now we will not be going into that. So once we understand that what is the meaning of first ionization enthalpy, second ionization enthalpy and third ionization enthalpy, we need to understand that the effect of the future ionization enthalpy is much more. I mean to say that much more amount of energy is required in the case of the second ionization enthalpy as compared to the first ionization enthalpy. Also, more amount of energy will be required in the third ionization enthalpy as compared to the second ionization enthalpy, that way. So because of the simple fact that if in case we already have a positively charged ion, it is difficult to remove an electron out of it, because in the case of say aluminum, we already have aluminum in its plus 1 oxidation state. One electron has already been removed from aluminum, and because aluminum has a plus 1 charge on it, it will have a natural tendency of becoming an aluminum atom again by accepting an electron. So it will try, as a matter of fact, to go reverse. That is, it will try to accept one electron and to form aluminum atom because of the formation of aluminum ion. And hence, if in case you try to do the reverse, that is, if in case you try to again remove one electron out of it, then you will have to give slightly more amount of energy. So hence, the second ionization enthalpy in the case of aluminum will be much greater than the first ionization enthalpy. So once we understand that, we understand what is the meaning of first, second, third ionization enthalpy and how the ionization enthalpy compares, especially when we are talking about the positively charged ions which are formed in the case of metals. Let us now look at the trends as we go from left to right in the periodic table. Okay, so let us write down. So as we go from left to right in a particular period, that is the situation A, is as we go from left to right in a particular period of the periodic table. Let us look at what the specific trends will be in this specific case. Okay. Let us have a situation wherein we are starting from say sodium. So if in case we are starting from sodium, then the ionization enthalpy in the case of sodium will be very less, right? Why it will be very less? Because sodium has only one electron in its outermost shell and it wants to desperately give out that electron. It will gain stability of its nearest noble gas, that is neon, if in case it gives out that electron to form the electronic configuration of its nearest noble gas, that is 2,8, as we have already seen in our last videos. So I'm not wasting time in writing down the electronic configuration for each of the elements that I'm talking about. So you guys need to understand what I'm talking. So after sodium, we know that because one electron has to be removed, in the case of sodium, the ionization enthalpy will be the least. It means least amount of energy will be required to remove the valence electron from sodium. If in case now we talk about magnesium, magnesium's ionization enthalpy, that is right now for the remaining part of the discussion, my dear friends, we will only be talking about the first ionization enthalpy, right? So that there is no confusion. We will not be talking about the second or third ionization enthalpy because that is a totally different part, and there we will be going much deeper. Right now we don't want to go that much deep. As of now, we will be talking about the first ionization enthalpy. So from now onwards, till the end of this part of ionization enthalpy, whenever I talk about ionization enthalpy, I by default mean the first ionization enthalpy, right? So after, in the case of, this is the situation in the case of sodium, the ionization enthalpy in the case of sodium will be very less. If in case we talk about in the next element after sodium, which is magnesium, in the case of magnesium, the ionization enthalpy will be slightly greater than in the case of sodium. In the case of after magnesium, if in case we look at aluminum, the ionization enthalpy will be slightly less in the case of aluminum. After aluminum, we will be having silicon, wherein the ionization enthalpy will be more in the case of silicon. In the case of phosphorus, again the ionization enthalpy will be more. In the case of sulfur, if in case we look at the ionization enthalpy, it will be slightly less than that of phosphorus. Finally, chlorine's ionization enthalpy which be much greater. And finally, we will be having the ionization enthalpy of argon, which will be the highest. So this will be how we will be having a pattern in terms of ionization enthalpy. So what we have here, my dear friends, is along the y-axis, obviously we have plotted the values for the ionization enthalpy. Now we know that the unit of ionization enthalpy is in terms of kilojoule per mole, and it is represented as delta H. So ionization enthalpy increases in this direction. Again, along the x-axis, we have an increase in atomic number. So therefore, here atomic number is represented, can also be represented by Z, right? So here we have atomic number. But here we are only talking about the atomic numbers. Say for example, in the case of sodium, we have atomic number 11, right? We are right now talking about atomic numbers from 11 to 18. That is, we are talking about the third period in the periodic table. So here we have 11, then 12, then 13, then 14, then 15, then 16, then 17, and then finally we have got 18. So this is how there will be a change in terms of the ionization enthalpy of different elements. First of all, this will be the specifics, right? Right now, let us draw a general idea about what happens when we go from left to right in the periodic table. After we go that from left to right in the periodic table, we will come to a conclusion about what happens in the specific atoms in each specific case. Once we go from left to right, after that we will go from top to bottom. Let us complete this part first quickly. Now, let us look at the effect of all these different factors as we go from left to right. Like say for example, as we go from sodium to argon in the periodic table. As we go from sodium to argon in the periodic table, what happens to the number of shells? The number of shells is the same, right? And because it is the same, it doesn't play any part in the ionization energy portion of the study. Hence, I have written equal to sign. It means it doesn't play any part or any role in the ionization enthalpy calculation from sodium to argon. Next, we will be calculating the effective nuclear charge. Yes, the effective nuclear charge as we go from sodium to argon, the amount of the nuclear charge, it increases, as well as the amount of electrons also increases. So in the case of sodium, we have total amount of electrons as 11. In the case of argon, we have total amount of electrons, outer electrons as equal to 8. In the case of sodium, the total amount of outer electron is equal to 1. And when we are talking about atomic size, my dear friends, we are talking only about the outermost electron, because the outermost shell, what is atomic size? Atomic size is nothing but the size, the distance between the outermost shell and the nucleus of an atom, right? So here we are only concerned about the number of electrons which are present in the outermost shell. So even though in the case of the outermost shell, the number of electron increases from 1 to 8, however, the nuclear charge, it increases from 11 to 18, and hence we can say that the effective nuclear charge, it increases as we go from left to right in the periodic table. And next, let us talk about screening effect. Because, my dear friends, all these elements belong to the same shell, therefore there is no question of screening effect, right? And therefore this point will also be a wash, that is, this point will be the same for all of them. There will be no effect, net effect of this point on the ionization enthalpy of these elements. Next, finally, we will be talking about the interelectronic repulsion. Yes, this will play a part in the ionization enthalpy. Now, let us talk about the interelectronic repulsion. As we go from left to right in the periodic table, that is from sodium to argon, we have more and more number of electrons which are formed, which are being added to the same valence shell, and due to which the interelectronic repulsion will increase as the number of electrons keep on increasing, especially after after phosphorus. So here the amount of interelectronic repulsion, it will increase in the valence shell as you move from left to right in the periodic table. Now let us now look at the So here we have finally the only two factors which have an effect on the ionization enthalpy as we move from left to right in the periodic table from sodium to argon. Let us look at both these factors and let us study the dynamics of both these factors and finally determine what will happen to the ionization enthalpy. So because of the increase in the effective nuclear charge, the electrostatic force of attraction, it increases, and hence the outer electrons, valence electrons, are pulled closer towards the nucleus. Again, the counter factor will be the interelectronic repulsion. As the number of electrons increases, because of the interelectronic repulsion, the atomic size will increase. If in case we consider the interelectronic repulsion factor. So let us write down the net effect of all of them. The net effect in the case of interelectronic repulsion will be that the atomic size should increase. Here the net effect should be that the atomic size should decrease. And we know that as atomic size increases, the ionization enthalpy, it decreases, and we know that as atomic size decreases, the ionization enthalpy value, it increases. Because first of all, let us understand the relationship between atomic size and ionization enthalpy, which is crucial for you to understand this part. See, as the atomic size increases, the electrons are closer towards the nucleus, right? And because the electrostatic force of attraction is more, hence the electrons are closer towards the nucleus. And when the electrons are closer towards the nucleus, I'm talking about valence electrons. When they are closer towards the nucleus, it is very difficult to remove that electron out, right? Much more amount of energy will be required to remove that electron which is strongly attached to the nucleus out of the force of attraction of the nucleus. And hence, as we can say that as the atomic size, it decreases, the ionization enthalpy it increases. Again, the opposite will take place if atomic size increases. If there is an increase in the atomic size, then obviously the outer electrons will be very much far away from the nucleus. If the outer electrons are very far away from the positively charged nucleus, then the force of attraction will be very less between them. In such a situation, it is very easy to remove that outer valence electron from the influence of the positively charged nucleus. Hence, the amount of energy which will be required will be very less. Hence, the ionization energy value will be very less. So this is the relationship, my dear friends, between the atomic size and the ionization energy. This relationship is crucial. Hence, we know that as we move from left to right in the periodic table, the atomic size, it decreases. Sir, how can atomic size decrease? Because according to interelectronic repulsion, the atomic size should increase. Yes, my dear friends, I know about it. However, we know that the net effect will be that atomic size decreases because the effect of nuclear charge is much more than the effect of interelectronic repulsion. We had seen that the atomic size exactly does not decrease all around. The atomic size decreases to a certain point, and towards the end, when we are talking about the noble gas, then the atomic size, it suddenly increases because of the interelectronic repulsion. So in general, when we go from left to right in the periodic table, as the atomic size decreases, hence the amount of energy which will be required to remove the outer electron will increase. So therefore, we know that as atomic size decreases, the ionization enthalpy that will be required, it increases. So this will be in general, the effect as we move from left to right in the periodic table. We will be going into specifics a while later. Right now, let us look at what happens as we go from top to bottom in the periodic table. That is when we go from top to bottom in a group in the periodic table. As we go from top to bottom in a group in the periodic table, then what happens is that the number of shells, it keeps on increasing. So let's write down what happens in this specific case on the right hand side of that factor, right? So what happens here is that the number of shell, it increases as we go from top to bottom in the periodic table, because the number of shell in the case of lithium is 2, and however the number of shell in the case of francium is equal to 7. So therefore, as the number of shells increases, the distance of the between the nucleus and the outermost shell, it keeps on increasing. In the case of hydrogen, it is very close to the nucleus. The one electron is very close to the nucleus. Lithium, one electron, one valence electron is slightly away from the nucleus. In the case of sodium, it is slightly away, still slightly away. In the case of potassium, it is still slightly away. In the case of rubidium, it is still slightly away. It is in the case of cerium, caesium, it is still slightly away, and in the case of francium, it is still the farthest from the nucleus. As you can see, in the case of francium, because the electron is present the farthest from the nucleus, it is very easy to remove that electron. The amount of energy which will be expended to remove that electron will be very, very less. So therefore, as we know that as the atomic size increases, that is, as the number of shells increases, the atomic size, it also increases. So therefore, as the atomic size increases in this specific case, as you move from top to bottom in the periodic table, the ionization energy will decrease. That is, very less amount of energy will be required. Hence, my dear friends, we can conclude that as we go from top to bottom in any group in the periodic table, we had considered, for example, the alkali metals, right? It can be any groups. In the case of halogens, in the case of alkaline earth metals, any group in the periodic table. As you go from top to bottom in a group, the atomic size will keep on increasing because of the increase in the number of shells, which is the most important factor which affects the atomic size. Hence, the atomic size increases. As the atomic size increases, the electrostatic force of attraction between the valence electron and the nucleus, it decreases. Hence, it is easier to remove the electron. It means less amount of ionization energy will be required to remove that electron. So this is the final relationship between them. There will also be might be some other factors which affect the atomic size and hence the ionization energy as we go from top to bottom in the periodic table, but those will not be that much important as compared to the number of shells, as we have already discussed. However, for formality, let us discuss each factor in this specific case. What happens to the effective nuclear charge? The effective nuclear charge obviously increases as you move from top to bottom. For example, in the case of lithium, the atomic number is 3, hence the total number of protons will be 3 inside the nucleus. In the case of sodium, number of protons will be 11. In the case of potassium, number of electrons will be 19, so on and so forth. And hence the number of protons will keep on increasing as we go from up to down. However, it is a less important factor as compared to the number of shells. Because of the number of shells, it is the most important factor which determines the atomic size of an atom. Hence, because of the effective nuclear charge, the atomic size actually should decrease, but the effect is much lesser. Next, when we are talking about screening effect, yes, here as you go from top to bottom, the screening effect becomes much more, and because the screening effect becomes much more, hence the outer electron is still therefore lesser bound towards to the positively charged nucleus, and hence because of the screening effect, the electrostatic force of attraction between the valence electron and the nucleus, it still decreases, and due to which the atomic size, it increases. Atomic size, it increases, as we know, the ionization enthalpy will decrease. So here the atomic size, it increases because of the screening effect part. Next, in terms of interelectronic repulsion, my dear friends, when we are talking about a particular group, the number of valence electrons which are present in a particular group will remain the same, right? Like in the case of lithium, sodium, potassium, rubidium, etc. So number of electrons in the valence shell of all of them is the same, hence which is equal to 1. Hence we can say that the interelectronic repulsion factor, it is a wash. It does not play any role in this specific case when we go from up to down in a particular group. So only these are the 3 factors which affect it, out of which because of the effective nuclear charge, the atomic size should decrease. However, because of the number of shells and the screening effect, the atomic size should increase. Because of the importance of number of shells, as we have already discussed, finally the atomic size increases, the ionization energy keeps on decreasing. This is again, as I've told you, this was in general what will happen to the atomic size and hence the ionization energy, first ionization energy, as you move from left to right and top to bottom in the periodic table. Now let us talk about specifics. The specific things that we need to talk about is why, as we move from left to right in the periodic table, the ionization energy should increase, right? So as we move from left to right, that is from sodium to argon, the ionization energy should increase. It is increasing, but as you can see, my dear friends, here you can see very clearly there are two different places where the rule is broken. The first situation where the rule is broken is in the case of aluminium. You will be able to understand this better once actually you understand the chapter of atomic structure, which I hope so you have completed and you have finished. There you understand something which is called as the concept of an orbital. Once you understand that, you will be able to understand right now what I am going to talk. Let us write down the orbital electronic configuration in the case of magnesium as well as in the case of aluminium. So in the case of magnesium, we know the atomic number is equal to 12, right? Hence, the electronic configuration can be written in terms of 282. Now, this will be the shell electronic configuration which is written. Right now, what we are going to write down will be the orbital electronic configuration which will be applicable. So, hence the orbital electronic configuration here will be 1s2, 2s2, 2p6, 3s2. Now, after writing this down, let us now try to write down the orbital electronic configuration in the case of aluminium. In the case of aluminium, we have total number of electrons which is equal to 13. Hence, the electronic configuration will be 282. In the case of aluminium, we will have all of them, but after that, we will also be having 3p1. Now, what happens, my dear friends, here in the case of aluminium is if in case we show the orbitals in the case of aluminium, let us see what happens. In the case of magnesium and aluminium, let us consider the valence electrons. So in this case 3s2, the orbital can be drawn like this. In the case of aluminium, we can draw the orbital of 3s2 like this, right? And once we finish drawing the orbital of aluminium, we can write down what happens in the case of 3p. In the case of 3p, we have the orbitals which can be written down as follows, which is like 1, 2 and 3. So because in the case of p subshell, we have got 3 orbitals, right? So we know that each orbital will have total number of 2 electrons inside it. So in the case of magnesium, the last 2 electrons which are present are like this. In the case of aluminium, the last 3 electrons which are present will be like this, and one will be entering the p orbital, specifically 3px orbital. Now, as we can see, in the case of aluminium, the one electron which is present in the p subshell, that one electron will not be that much stable, because electrons are stable only, we know from atomic structure chapter, when the particular subshell is either half filled or a particular subshell is either completely filled. If in case we had a situation wherein 1, 2, 3, there would have been 3 electrons of one spin itself, so it would have been half filled, then it would have been stable. Or other way around, if in case we have it as completely filled, wherein we have one electron in the upper direction, one electron in the lower direction, here and here. All the orbitals of this p subshell, if it would have been completely filled or even half filled, it would have been stable. In this specific case, it is not stable because there is only one electron which is present in p subshell, and this one electron is very vulnerable. It can very easily be removed because it is not very strongly attached to the nucleus, and hence in the case of aluminium, this first ionization enthalpy will be very less as compared to in the case of magnesium. In the case of magnesium, as you can see, this orbital is completely filled, and hence we have a situation wherein it will require much more amount of energy to remove one electron out of the orbital in the case of magnesium when we are talking about the valence electrons. So hence this explains why in the case of aluminium, the ionization enthalpy, the first ionization enthalpy will be less as compared to in the case of magnesium, because this one electron in the case of aluminium can very easily be removed. Once we have understood what happens with in the case of aluminium, we also have another situation wherein we are talking about sulfur. In the case of sulfur, my dear friends, also we have a situation wherein its ionization enthalpy, it should be greater than phosphorus, right? Because it should increase now as we go from left to right. The ionization enthalpy should increase. However, the ionization enthalpy of sulfur has decreased from that of phosphorus. Let us consider the reason for that. To understand the reason for that, also we need to write down the electronic configurations as we have done in the case of magnesium and aluminum. In the case of phosphorus, first let's write down in the case of phosphorus what happens. Phosphorus atomic number 15, electronic configuration 285, orbital electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p3. Let us now look at what happens in the case of sulfur. Sulfur atomic number is equal to 16, electronic configuration 286, orbital electronic configuration, the same thing from here to here. I am not wasting time writing them down. Again, finally, we will be having here as in the outer situation, it will be 3p4 because it has one more electron as compared to in the case of phosphorus. Now, let us write down the orbitals which will be applicable in the case of phosphorus as well as in the case of sulfur. If we write down the orbitals, it will be somewhat like this. In the case of phosphorus, the p orbital can be represented like this, right? In the case of sulfur also, the p orbital can be represented in a similar way. Let us now draw the different orbitals. So here also we have drawn the different orbitals which will be applicable. So therefore here in the case of phosphorus, we will be having 3 electrons which are present here. So therefore this is the first electron, this is the second electron, and this is the third electron. In the case of sulfur, we will be having 1, 2, 3 and finally 4 electrons which are present. Now again we go back to exactly what I had taught you in atomic structure chapter, which I am repeating again. When we have a situation wherein a particular subshell has the different orbitals which are present in a particular subshell, all the orbitals have are either singly filled or doubly filled. In that case, it will result in stability. So here the p subshell is half filled, and hence the stability here will be much greater. In the case of p subshell, you might argue, sir, even this is half filled, right? However, this is half filled, but it has one more electron, and because it has one more electron, this second electron can very easily be removed. Hence, we have a lesser stability here in the case of sulfur as compared to in the case of phosphorus, as regarding the strength of the most easily detachable electron. When I am talking about strength, the strength of attraction between that most easily detachable electron with the positively charged nucleus. So because in the case of sulfur, this electron can very easily be removed because of the instability involved. Hence, the first ionization enthalpy in the case of sulfur is lesser as compared to in the case of phosphorus, where it is very difficult to remove any electron from the very stable half-filled electronic configuration of phosphorus. So this explains why sulfur has lower ionization enthalpy as compared to phosphorus. So in general, we can say that as the atomic number increases, the ionization enthalpy increases as we go from left to right in the periodic table. But practically speaking, this is exactly what happens. Now, once we have understood this, we also finally, as we have already discussed, as we move from up to down in the periodic table, the ionization enthalpy will decrease. But again, it will not be a straight line graph decrease. It will decrease, there will be no exceptions. However, there will be no exceptions, but the decrease will be in the first situation. If the decrease is very steep, in the second case the decrease will not be that much steep. However, there will be a decrease. There is no exception in the case of a group. Finally, before finishing the portion of ionization enthalpy, we will now need to understand what happens with in general in the periodic table. So as you can see, in general in the periodic table, if in case we start with hydrogen, this is the ionization enthalpy in the case of hydrogen. In the case of hydrogen, the ionization enthalpy will be this much, which is still greater. But however, in the case of helium, because it's a noble gas, hence the noble gas is extremely stable. So it requires huge amount of energy to remove an electron from a stable noble gas. Hence the amount of ionization energy in the case of helium is very great. And that is the same trend is followed in the case of all noble gases. See, I have shown all the noble gases one after the another. Again, the ionization enthalpy will be the least in the, as you can see, the noble gas, it will be the greatest. Ionization enthalpy will be the least in the case of alkali metals. So as you can see, all the alkali metals have been shown down. So here we have lithium, here you have sodium, here you have potassium, here you have got rubidium, here you have got caesium, cesium, here you have got francium. So as you can see, there is a particular trend when we are talking about the alkali metals. As we move from lithium to francium, the amount of ionization energy, as you can see, it is decreasing. Again, in the case of noble gases also, the ionization enthalpy, as you can see, is decreasing as we go from top to bottom in the periodic table without an exception. However, we now have a situation wherein in the case of lithium, this is lithium, this is beryllium, this is boron. This is then again after boron we have carbon. This is carbon. This is again nitrogen. This is oxygen, right? This is nitrogen. This is oxygen. This is again beryllium. This is boron. As you can see, from beryllium to boron there is a slight decrease. In the case of nitrogen to oxygen there is a slight decrease, which is exactly what corresponds to the decrease which I have shown you here, which exactly happens in the case after sodium. We have here magnesium, right? This is magnesium and this is aluminum. As we see in the case of aluminum, there is a decrease which is shown here. The same decrease and the same reason will be applicable when we go from beryllium to boron. Why in the case of boron, the ionization enthalpy will be less as compared to in the case of beryllium? The reason is the same as the reason why aluminum has lesser ionization enthalpy as compared to magnesium. Again, we have, after aluminum, we have got silicon here. We again have phosphorus here and we have sulfur here. As you can see, again sulfur has a lesser amount of ionization enthalpy as compared to phosphorus. The reason I have shown you here, the same reason can be exported to explain why oxygen has lesser amount of ionization enthalpy as compared to nitrogen. And the same thing here, as you can see, in each particular part we have the same situation wherein there is a slight decrease at two different portions of the graphs, right? So as you can see, the same pattern is repeated, and hence these are called as periodic properties because these properties change with in periodic nature. So just to show you one particular property again, in the case of sodium to argon, we have seen that in the case of sodium to magnesium, the ionization enthalpy has increased. From magnesium to aluminum, the ionization enthalpy has decreased. From aluminum to silicon, the ionization enthalpy has increased. From silicon to phosphorus, the ionization enthalpy has still increased. From phosphorus to sulfur, the ionization enthalpy has decreased. And then from sulfur to chlorine, the ionization enthalpy has further increased. I have not shown the dot of chlorine. It will be somewhere here. After chlorine, the ionization enthalpy will further increase and it will reach its maximum at the noble gas. Again, after we reach the noble gas, when we go to the next shell, the ionization enthalpy further decreases because again we have potassium, which is alkali metal. In the case of alkali metals, because it has only one electron, as we have already seen, it is very easy to remove electron, hence the ionization enthalpy is very less. So hence the potassium being alkali metal, the ionization enthalpy, it drops drastically from the noble gas to the alkali metal, which is present as the first electron in the next shell. So this, my dear friend, was everything that you needed to know about the ionization enthalpy part and the trends of how it keeps on changing in the periodic table as you move from left to right and from top to bottom in the periodic table. Friends, let us now solve a very small numerical related to the ionization enthalpies or ionization energy. We know that energy and enthalpy terms are used interminably here, and you can use any term you want. It basically means the same. So here we have been given in this question the ionization energy of sodium, magnesium, silicon, and we have been asked to estimate if the value of ionization enthalpy of aluminum, if it will be closer to 760 kilojoule per mole, or it will be closer to 575 kilojoule per mole, keeping into mind the ionization enthalpy of the remaining element which has been given to us. So basically here we need to not just find out the answer, but also give the correct reasoning behind those answers. So what I want you guys to do is just pause this video for some time. Just try to get the answer and the explanation for the same, and we'll meet on the other side of the video with the solution. So friends, let us now start solving this question. Now here we know very well that in the case, first of all, we know two facts. Point number one, important fact, is that the value of ionization energy is always positive. You will never find the value of ionization enthalpy as negative, because of the very simple reason that whenever we have to remove an electron from the valence shell of any electron, that is the most easily removable electron is actually removed by supplying some amount of energy, right? So some amount of energy is always required here. Energy is not liberated here. Energy has to be supplied. So therefore, in this case, it is an endothermic process. And because here we have an endothermic process, hence we have a situation wherein the value of ionization energy can never be negative. Point number one, finished. Point number two, we here also need to understand what I have told you in the case of explanation of ionization enthalpy, that the electrons belonging to the S subshell, they are attracted towards the nucleus much more strongly as compared to in the case of electrons of say any other subshell like P, D, F, etc. So this is one thing which you also need to keep in your mind. Now applying that knowledge, let us now calculate what will be the ionization enthalpy in the case of aluminium. Approximate will be the correct word to use instead of calculate. So here we have the ionization enthalpy of sodium, which is 496, which is expected. It has to be very less, because we know that in the case of sodium there is only one electron which is available, which can very easily be given off. So obviously very less amount of energy is required to remove that most easily detachable electron there, which is just that one electron. However, in the case of magnesium, we see that suddenly the amount of ionization energy has increased to 737, which is a very large value. To understand what's going on, my dear friends, you actually need to write down the electronic configuration. In the case of magnesium, the orbital electronic configuration. My dear friends, we have already done this, so I'll be going a bit fast. So please catch up with me. So here in the case of magnesium, we know that the orbital electronic configuration will be 1s2, 2s2, 2p6, then 3s2 in the case of magnesium. So if in case we write down the outer electronic configuration in terms of the drawing of orbitals, it will be somewhat like this. So here we will be having the 2 electrons of magnesium, which can be represented here. So here electron I am representing with orange color. So here we have total 2 electrons which are present in the outermost subshell of the magnesium atom. So as you can see in the case of magnesium, because the 2 electrons are filled in one orbital, so this orbital is completely filled. And as I've already told you many times over, and as you have learned in atomic structure chapter, when any orbital is completely filled, then we know that there is a huge amount of stability involved, especially when S subshell is involved. As I have told you, when electron is in the S subshell, it is closer to the nucleus, hence the electrostatic force of attraction with the nucleus is very, very strong as compared to the other orbitals or the other subshells like P, D and F. So here in the case of magnesium, this results in a high ionization energy value. However, in the case of aluminum, let us see what happens. If in case we write down the electronic configuration of aluminum, we will be having a situation wherein up till here it will be the same, right? Electronic configuration will be the same. Here we will be having 3s2 and here we will be having 3p1 in the case of aluminum. As we have already seen, my dear friends, what happens here is that we can quickly write down the the orbitals here. In the case of aluminum, there will be just one orbital here, right? In the case of aluminum, you will be having here 3p, there will be 3 orbitals here in the case of p subshell, as we already know. However, let us now quickly put the electrons into these specific orbitals. We know that in the case of aluminum, we have 3s to 3p1 electronic configuration, so there will be 2 electrons here and 1 electron here. However, this electron can very easily be given away, and especially because this electron belongs to the p subshell, and because this electron can be very easily be given away, hence we have the ionization enthalpy in the case of aluminum, which should be very less as compared to in the case of magnesium, and which will be comparable to that of the case of sodium. And hence, my dear friends, here we will be having the ionization enthalpy of aluminum, which will be very less, which will be comparable to the in the case of magnesium, and which will be very less as compared to in the case of magnesium. Hence, the only value which satisfies this conclusion of ours will be 575 kilojoule per mole, because it is closer to in the case of sodium, and it is very less as compared to in the case of magnesium. In the case of silicon also, since the value is given, I need not show it to you, but since the value is given, let us also see what happens in the case of silicon. So if in case instead of aluminum, if in case we had silicon, in that case we would have had one more electron here. So in the case of silicon, because there is one more electron here, the amount of energy which is required to remove this electron in the p subshell would have been slightly much greater as compared to in the case of aluminum, where only one electron was to be removed. Because here two electrons are still there, there is slightly more amount of stability which is involved. So I hope so, my dear friend, that you were able to solve this question correctly. Congratulations if in case you have.